Catching the maximum possible amount of flow happens when you hold a physical boundary directly against the current, but rotate that same ring 90 degrees and the particles bypass it entirely. Though the stream hasn't changed, the capture drops to zero. Our instinct is to capture more field lines by making the surface bigger or increasing the field strength. Yet orientation dictates the final result. Tilting the surface determines how many lines cross the boundary, regardless of field strength. Interaction between a field and a surface requires a specific spatial relationship. This raises a geometric question. How do we mathematically define the direction a flat, two-dimensional sheet is facing? Standard area calculations only provide a magnitude, a flat number that lacks spatial awareness. It tells us the size, but not the orientation. To solve the flow problem, we have to look at area as something more than just a scalar value. In fluid dynamics, the rate of flow is defined as the volume of liquid crossing an area per unit of time. Static electric fields do not physically move like water. Instead, we measure the density of field lines piercing a unit of area. We define the direction of this surface using a normal, an arrow pointing perfectly perpendicular to the plane, labeled here as delta S. For closed three-dimensional shapes, the convention is that this arrow always points outward from the interior volume. This gives area a specific direction. It is now a vector, possessing both a magnitude and a defined orientation in space. Tilting the area vector creates an angle, theta, relative to the incoming electric field lines. The field interacts only with the projected area, the reduced silhouette created by the tilt. As the angle increases, this silhouette shrinks. Multiplying area by cosine theta isolates this perpendicular silhouette. The field ignores the physical surface and only interacts with the portion aligned to face it. Combining the field strength with this projected area gives us the complete equation for electric flux. This arrangement of variables is the mathematical definition of a vector dot product. The dot product provides the mathematical bridge needed to calculate the geometric alignment between two different directions. Parallel vectors yield the maximum possible flux, while a 90-degree angle results in a flux of zero. Using the outward normal convention for area vectors is essential for solving electrostatic field problems correctly. This specific logic scales up from flat planes to accurately map the invisible fields surrounding complex, closed three-dimensional shapes. Mastering this specific geometric alignment is the final step toward applying Gauss's law in the next chapter.